Hi everybody, welcome to section 1.5, linear equations, zeros and applications. Let's get right to it. So this is example number 1, and you can see there's a couple fractions, and I think the best thing to do whenever you see fractions is to, or often whenever you see fractions, was to clear the fractions. The least common denominator between 4 and 5 would be 20, so I think it might be a little, at the very beginning, it might be a little difficult to clear the fraction because you have to multiply 3 different terms by 20, but when you do that, you get something a lot easier to handle. 3/4 times 20, you could even draw a line under 20 and put it over 1 and cancel. Line over 20, 20 over 1 and cancel, and you could see that you get 15x minus 20 equals 28. Adding 20 to both sides, you get 48, and dividing both sides by 15, you get 48 over 15, which simplifies to 16/5, or if you like decimals, 3.2. Interestingly enough, if you wanted to, you could split up the two halves of this equation into 3/4 x minus 1 and 7 over 5. You could, those are the two halves of this original equation, and if you set them both equal to y, you get two lines you could graph. And the interesting thing about what happens when you graph these, so feel free to copy this down, is that they intersect right exactly what the value of x is. Remember, we solved the equation, we get x equals 3.2, and so what this really means is anytime you're trying to solve an equation, if you really wanted to, you could just reach over to your graphing calculator, go to Desmos.com, and you could graph each of the two halves separately as two different equations and get the answer in the x value right here. When x is 3.2, then all of a sudden this equals this, which is great news, especially if you ever need to check your answer, or if you ever are given an equation that's just beyond your algebra to solve for whatever reason. I mean, there are lots of equations out there that are even beyond my algebra to solve, or anyone's theoretical algebra to solve, because they're just too complex. Why not just graph them? Okay, anyway. Example 2. Here we've got a bunch of parentheses. Maybe it would be a really great thing to do first to just distribute. So you get, when you distribute this 2, you get 10 minus 6x equals 8 minus 3x minus 6. And then combining these 8 and minus 6, you get 2. 10 minus 6 equals 2 minus 3x. By the way, if this is ever confusing exactly what to do, like should I add the 8 and the 6 or should I subtract them, I always think it's a lot easier to convert all subtraction to addition. I didn't do that here, but you can if you want. The subtraction could become plus negative 3x plus negative 6, and then 8 plus negative 6 is a little bit easier to handle if you wanted to. Anyway, the answer is 2 right here. And so then combining the terms on both sides, you get, when you add 6x, you get 10 equals 2 plus 3x. Subtracting the 2, you get 8. And dividing both sides by 3, you get 8/3 equals x. And as a decimal, that's 2.6 repeating. Same idea before. If you wanted to, you could avoid all this solving by simply reaching for a graphing calculator and putting this part in as y1 and this part as y2. It would look like this, y1 and y2. And when you graph them, the intersection provides the answer. You remember it was 2.6 repeating? Well, here it is. That's the x value. So when x is equal to 2.6 repeating, all of this will equal all of this. And in fact, the value would be negative 6 if you really wanted to know what it is. So there it is. Let's do one more example to illustrate another point, what it looks like to have no solution. There's some equations out there that will never yield an answer. For example, an even simpler version of this idea would be just x equals x plus 1. There's no number on the number line that could possibly make x equal to x plus 1. There's just no solution. It doesn't work. And there's lots of other equations that are like that. Look, you notice this is basically the same equation written twice, negative 24x, and this is a 7 and this is a 17. Look, and when you add 24x to both sides, you get the numbers, the variable completely drops out, and you're left with something that's not even true. 7 just isn't equal to 17. When something like that happens, you can say that there's no solution to this equation. So, doing what we did before, split both up into, reach for the graphing calculator, put each half of the equation in for y1 and y2, and you notice something right here. You get train tracks. These are really cool parallel lines, and they're not going to intersect at all, ever. This has the y-intercept of 7. This has y-intercept of 17. They're just not going to intersect. There they are. So because there was a solution here, and it occurred at the intersection, there's no solution here because there's no intersection. Intersections and solutions are very much related. Next, look at this. These are the two halves of the same expression, just rearranged. This is a 3, you see a 3, a negative 1/3 x, a negative 1/3 x. But when you go to solve this, you could add 1/3 x to both sides. You get 3 equals 3. Some people might even want to subtract 3 from both sides to get 0 equals 0. Well, I got a news flash. It doesn't matter what value of x you choose in the original. You're always going to get something that's true. So this equation is true if you chose x equals 0, or x equals 1, or x equals 10, or x equals a negative million. It doesn't matter. You plug it in to the equation, you're going to get the same number on both sides. Or then, an even simpler version of this situation would be x equals x. The equation x equals x, just like this equation, has an infinite number of solutions. You could put in whatever number you want in for x, and it's just going to work as an equation. So, yes, like it is right here. You can see x could equal all these numbers, and the equation will be true. It'll be a solution, just like when x equals x. This is an equation you could try to solve, but there's infinite solutions. Well, you could reach for the graphing calculator, desmos.com, plug in 3 minus 1/3 x, that's the left-hand side, and then the right-hand side of the equation, as two separates. Why do I keep doing this? And notice that they are graphed on top of each other. These are two lines independently graphed, the red and the blue, and you notice that they exist in the same space on the graph. They are overlapping completely. So this x value is a solution, this x value is a solution. All these points represent all the solutions, and there's just an infinite number of them. We've got the motion formula, d equals rt, dirt. This is a really super handy formula to memorize. Make sure you can write it, always write it down, d equals rt. Distance equals rate times time. So example 7. Delta Airlines fleet includes B 737-800s, each with a cruising speed of 531 miles, and Saab 340Bs. So B 737 and Saabs. Big jet, small jet. And the small jet has a cruising speed of 290 miles per hour. Suppose that the small jet, Saab, takes off and travels at its cruising speed, and 1 hour later the big jet, 737, takes off and follows the same route. Traveling at its cruising speed, how long will it take the big jet to overtake the little jet? So here's a great picture that the textbook gives you. You can see here's the starting line, here's the ending line, and we don't know how far away the ending line is. We just know that there's an unknown amount of time, t, and the Saab gets an additional hour because it started earlier. I've seen people write it as this could be t minus 1 and this could be t, if you want to let t represent the amount of time in the Saab. But we want to know what we really want to know is how long will it take the B737 to overtake. So the answer we're looking for is t, because that's the Boeing's time, not the Saab's time. The Saab gets t, Boeing's time, plus an hour. So what do we know? Let's organize ourselves. We know the rate of the Boeing, we know the rate of the Saab, and we know that the the Boeing gets one additional. The rate of the Boeing, it starts 1 hour later. So, and the things we don't know is the overall distance. We don't know how long it takes to go from there to there, from start to finish. We don't know the time, t time of the B737. And if we knew that time, we could add 1 to it to get the Saab, but we're just going to let t be our one unknown. I really like to organize my knowns and unknowns into this handy-dandy chart. It's always got 3 columns for my 3 variables, d equals rt. And because I've got 2 runners in this race, 2 jets, I'm going to have 2 rows here. D equals rt, d equals rt. And you don't you don't have to do this, but especially when things get way more complex, it's going to be a lot easier to keep everything organized visually right here. It helps force me figure out what goes in each box. If I don't know, because filling up the box with something is really important, even if it's just a variable. That way, once you fill the box, you know that you've addressed each part of the equation one time. So d equals RT, d equals 531 t, d equals 290 times t plus 1. Once you see that, once you fill in the box and decide on every part of all three parts of both equations, then you can say that you can start solving a system of equations. And here you can use substitution. You can say if this is equal to t and this is equal to t, then they should both, if this is equal to d and this is equal to d, then the two equations should equal each other. 531 equals 290 t plus 1. So there's three related ideas that I wanted to mention. And people often get these things confused because they're so related to each other that it's hard to even distinguish what the difference is. So let's say you had this expression 2x minus 4. And let's just say you set it equal to 0. The solution of the equation, when it equals 0, you're basically asking the question, if you want to find the solution of the equation, it's asking the question, what value of x solves the equation? You can find x by adding 4 and dividing by 2 and get the answer, which is 2. Now, if this were in a function form, if f of x equals 2x minus 4, it's the same expression, then sometimes you see instructions say, what are the zeros of the function? And basically, what that is asking is, the zeros of the function are the values of x that make f of x equal to 0. So very similar, if when f of x equals 0, you drop down into this equation, you can add 4 and divide by 2 and get x equals 2. The 0 of this function is very related to the solution of this equation. And if you were to graph it, not f of x but y equals 2x minus 4, then you would find, along the x-intercept, you would find the value of x equals 2. Where does the graph of f of x touch the x-axis? It touches it at 2. And how do we know? It's because you take 0 and plug it in here and solve, and you get x equals 2. These three ideas show up, are interrelated all the time, and it's good to make sure you understand that you can answer all three of these questions by doing the same thing. You basically solve the equation 2x minus 4. But they show up in three different areas. If you're talking about functions, then the terminology is zeros. If you're talking about solving equations, it's just there's only one variable right here. If you're looking at graphically what it looks like, it shows up in the x-intercept. Okay, another word problem. The simple interest formula. Interest equals the principal times rate times time. The starting principal amount that you invest times the interest rate times the amount of time that you leave it in will give you interest. This is actually not how any bank works ever, anywhere, but it's a simple version to help get us started in the wide world of finance. So, example 8, Damarian's 2 student loans total $12,000. So he's got two different loans. We don't know what they are individually, but when you add them up, you get $12,000. One loan is 5% simple interest, and the other is at 8% simple interest. After 1 year, Damarian owns $750 in interest. What is the amount of each loan? Okay, so the things that we know are, we don't know what the principal 1 and principal 2 are. That's what is the amount of each loan? That's the amount, P. So, and he's got 2 of them. We don't know what P1 and P2 are. But we do know that when you add them up, you get $12,000. And so therefore, maybe even more important equation would be if you solved one of them for the other. If you subtract P1 from both sides, you get this. P2 is equal to 12,000 minus P1. We're given that the rates are 5% and 8%. You can express it right here. Rate 1, rate 2. And then we also know that the total amount of interest owed at the end of the year is $750. After 1 year. So t equals 1 year, I1 plus I2 is 750. Since we have this formula, one thing I can do is say that the interest 1 plus the interest 2 would be the same thing as PRT1 and PRT2. when you add both of these expressions up, you'll get 750. And now I know most of these. I know what the rate 1 and the time 1 and the rate 2 and the time 2 are. I fill them in here. And then instead of, and then I don't know what P1 is, but I'm going to use this equation right here to figure out what P2 could be. The strong motivation for doing this is that now we've written an equation that only has one variable. And so we can solve. You can kind of multiply and distribute and combine like terms and subtract 960, and you get negative 0.03 P1 is equal to negative 210. And we divide both sides by negative 0.03, you get P1 is equal to $7,000. So if P1 is $7,000, you can put it in this equation right here and get that P2 is $5,000. So that's the section. I wanted to mention that back in high school, I was on the soccer team. I played soccer my whole life. Actually, I was a captain my senior year. It was a great fit. They were terrible and I was terrible, so that's why they made me the captain. It was awesome, and that's your audio check for today. Make sure you finish the assignment, the first problem of the assignment that's coming up in your composition book, and I will see you in class.